So this section we talk about convergence and divergence criteria, but the deeper theme here is the way that we use logic in communication. So when we explain mathematical concepts, just using plain English to our students, sometimes we introduce ambiguity, or sometimes we can even introduce logical errors. So when we're teaching, we want to be careful about the following three things, which we hope is the same, but could sometimes be different. There's what we intend to say, what we actually say, and then what our students interpret from what we say. Ideally, these three things are all the same, but of course we know that that's not always going to be the case. And so in this section, we're going to talk about divergence criteria, but we're sort of looking at it through the lens of how do we say certain things to students in such a way that helps us to ensure that what we're actually saying and is what we mean to say, and that our students interpret it correctly. So there's three main types of confusions that we're going to talk about. Of course, there could be other different sort of logical confusions that students could have. But the three that we'll talk about is we'll call the if and only if confusion. IFF is shorthand for an if and only if, or a biconditional statement. And this confusion happens when a biconditional or an if and only if statement is presented as one directional, right? As just an if statement. Right? We sometimes use like this arrow as opposed to an if and only if, which we use like a double-sided arrow. In that case, students may not know if both directions are intended, and so they might be confused about when and how they can sort of use these certain definitions or properties. The second type of confusion we could see is the is confusion, and that's when we're using is in order to connect two mathematical ideas without specifying the direction of the implication. So we might say like, an isosceles trapezoid is, and then state something that's, maybe just a property of isosceles trapezoids versus a definition, or versus something that, is true, but, maybe not qualifying as a definition. So without specifying the direction of the implication. Finally, the converse confusion occurs when students interpret a statement of the form Q if P to mean if P, then Q. As stated, the statement Q if P really means, this is incorrect. If they interpreted that as if P then Q, then they were correct. But sometimes students will interpret it as if Q then P. Q if P really means if P then Q, but it's not hard to see that students might jump to the wrong conclusion here and think that that means that if Q is true, then P should be true. In other words, they might think that you mean the converse of what you're actually trying to say. So how do we avoid these pitfalls in logic? One way to do that is to try to reframe the statements in a more formal way. So we can try to help reduce any ambiguity by making sure that we're actually writing our statements in a precise and logical form. A conditional statement of the form, we read this as if P then Q, is often used to describe a property or to give a criteria or criterion for something being true, depending on what you're saying about P or Q. And biconditionals, which we read as, or I should probably mention this, is if P, then Q. Biconditionals, which we read as P, if and only if Q, are more often used to either give a definition or to give some kind of an equivalence. Right? Some property holds if and only if, definition. If and only if some other property holds. So if we mean something to be a biconditional, we want to make sure we're really clear about stating that, either by stating it as an if and only if, or maybe just by stating it two times, stating the original conditional statement P implies Q, and then also stating the converse, Q implies P. So let's look at an example using convergence. So here's three statements, all of which maybe have an intended meaning that may or may not be true, but which could be interpreted potentially in a wrong way. So the first statement says, a sequence is convergent if all of its subsequences converge to the same limit. Second statement says, a convergent sequence is a sequence that is bounded. And the third says, a sequence is convergent if it is monotone and bounded. So I want to see where we might find some of these, some of these common types of confusion within these. So the first statement says a sequence is convergent if all of its subsequences converge to the same limit. That could be interpreted by students as saying, if all subsequences converge to the same limit, then the original sequence also converges to that limit. Which, okay, it turns out, is a true statement. It's not a particularly meaningful or a helpful statement. It's kind of a trivial statement because if that hypothesis, if the first part, all subsequences converge to the same limit, is true, then, well, that means the sequence itself is technically a subsequence of itself, has to converge to that limit. So obviously the original sequence is going to converge to that limit. So it's a true statement, it's just a kind of a trivial statement. I think probably what we mean to say, the more interesting part of this is really the converse of that, or really it's the fact that because both of those are true, should be stated as an if and only if statement, right? That a sequence is convergent if and only if all of its subsequences converge to the same limit. Or more importantly, just the more interesting direction of that says that if a sequence converges to some limit L, then all of its subsequences converge to that same limit L, which we call the subsequence convergence theorem. So this first one is really an example of that if and only if confusion, because it really is an if and only if statement, but it's not clear the way that we stated it that is the case. Let's look at the second statement. A convergent sequence is a sequence that is bounded. So this is actually called the boundedness theorem, and it's true, but its converse is false. So when we just say a convergent sequence is a sequence that's bounded, it can lead to a little bit of confusion because students might not mean that every sequence that's bounded is convergent, which is false, right? Or a convergent sequence is, or if it is convergent, then it is bounded, right? So, this is, I should write it down, this is a boundedness theorem. And we would just want to make a note that the converse to this is false. And so this could be an example of that converse confusion that we saw before. Finally, our third statement says a sequence is convergent if it is monotone and bounded. This is the monotone convergence theorem. And whoops, I should really say this is sort of the is confusion. The last one, the monotone convergence theorem, which says that a sequence is convergent if it is monotone and bounded. When we say it that way, a student might read this and say, okay, so if a sequence is convergent, then it's monotone and bounded. Well, that's not actually necessarily going to be the case. It doesn't have to be monotone and bounded. And so this is sort of our converse confusion here, where we stated the if part in the middle, when what we really mean is that if it's monotone and bounded, then it is convergent. So this is the monotone convergence theorem, and we're going to write these in a more clear way shortly. Okay, but this is our example of a converse confusion. Okay, so let's try to reframe these as if and only if statements, or as maybe they're more meaningful conditional statements that are implied there. So the first one, the subsequence conversion theorem, really says that if a sequence AN converges to some limit L, then that means that all subsequences of that original sequence converge to the same L. Again, it's worth pointing out that the converse of this is true. It's just kind of trivial. So you could state this one as an if and only if you wanted to, but this is a direction that's more interesting. The boundedness theorem, a restatement of statement 2, says that if AN converges, if it's a convergent sequence, then that means that we can conclude that AN must be bounded. And the third statement says that if AN is monotone and it's bounded, then we can conclude that AN converges. At this point, it's useful to point out that when we have statements like these, theorems that are very useful to us, oftentimes it can be helpful to look at the contrapositive of those statements. If we haven't talked about contrapositive or you hadn't thought about it in a while, a statement of the form P implies Q is equivalent to its own contrapositive, which states if not Q, then not P. Right? These statements are equivalent to each other. A statement's not equivalent in general to its converse. P implies Q is not equivalent to Q implies P, but it is equivalent to its contrapositive. And so if we have something that's a theorem that's been proved, not by us, but you could go to analysis textbook and read a proof of this, then its contrapositive is guaranteed to also be true. And those contrapositives give us some of the divergence criteria that we were referring to earlier in the video. So let's look at the contrapositives of each one of these three statements and then talk about whether this qualifies as what we call a criterion for divergence or not. So the first statement, the subsequence conversion theorem, when we take the contrapositive, we swap the if and the then, we negate each part, and we get a statement that says if not all subsequence of AN converge to the same L, in other words, if there is some, right, at least one subsequence of our original sequence AN which does not converge to L, then AN does not converge to that L, or to any L in that case. Okay, so the contrapositive of the boundedness theorem of statement 2 says if AN is not bounded, then AN does not converge. So if a sequence is not bounded, then it does not converge. And finally, the contrapositive of the monotone convergence theorem says if the sequence AN does not converge, then, now I need to negate this statement here, then that means that it is not the case that AN is monotone and bounded. That doesn't mean that it's not monotone and it's not bounded. It just means that it's failing this and statement, which means at least one of those two things must be false. So we would say something like, if the sequence AN does not converge, then AN is not monotone or not bounded, or potentially both. So I'm just going to take a moment to describe which one of these is what we would call a divergence criteria. In general, when you have a statement of the form P implies Q, in this case, the divergence is what we're looking for. And so if you have a statement of the form, like let's say, if a sequence diverges, then some statement Q is true. This really gives us a description of a divergent sequence, as opposed to if divergence is the conclusion of your conditional statement. So if you have a statement of the form if P, then a sequence is divergent, then this is what we would call a criterion, or gives a criterion for divergence. So notice that in our first two statements, because the divergence comes as the conclusion, as the then part of it, right? Does not converge. That means that these first two are what we call divergence criterion. Whereas the last statement, the convergence comes at the beginning, right? That's part of the divergence comes at the beginning. It's part of the if of the statement, which means that this is not a criterion for divergence, but instead it's giving a description of divergence, right? If it's divergence, then we can say that that sequence is either not bounded or not monotone, or potentially neither one. Okay, so just to sum up here, by reframing our statements using formal logic, using that if-then or if and only if language, we're able to reduce ambiguity in our teaching, which is always helpful, right? Ambiguity just gives ways for students to misunderstand. It makes logical structure more transparent, and as we saw on the last page, it allows us to clarify when we're stating definitions versus looking at properties. And also, it shows us how theorems can be turned into either like criterion or giving descriptions of certain things. And so we'll talk about this a little bit more in the exercises.